My name is Mark Scythian. The date today is June 11, 2025. So this presentation is going to focus on geometric shapes, formula shortcuts. So instead of having too many components, we can consolidate the components, the constants in a given equation and then work with the variables. So for example, if you're dealing with the area of an ellipse, we would first bisect the ellipse to find the center point on the vertical and horizontal axis, the y and x axes. So now we got a center point. So then the vertical member is A, horizontal B, of 1/4 section. So then it's just pi times A times B. So if we work this out, we'd calculate 11.31 square inches as the area of this given ellipse, but we could also rewrite this as 3.14159 AB. So 3.14159 is the constant pi. So then we move on to volume of a cone. So we're basically finding the volume of a cylinder times 1/3. So 1/3 the volume of a cylinder is the volume of a cone. So if we were to use the conventional method, we would just take the pi r squared, the radius squared, then times the height, and then times 1/3. But we could also use the shortcut method, 0.25905 times diameter squared, so 10 times 2, 20-inch diameter squared, then times the length. In this case it's the height, so 38 inches, and then we calculate this value here. So we can check the consolidated method. So there's your pi r squared, area of a circle, times the height or the length, and then times 1/3, 0.33. So we calculate the same value approximately. So that works. So of course the area of a cube is pretty straightforward. Length times width times height. So let's say a 10 square cube, 10-inch square cube. So 10 times 10 times 10, 1,000 cubic inches. So the difference between a square and a parallelogram is that the parallelogram is like the square, but it's like as if you've got hinges on the corners. Like if this was a collapsible chair, and before you put the third number, you notice the corners, let's say, have hinges. Now you just kind of stagger and turn the square into a parallelogram, and so its actual area is the same as the formula for area of a square. So if you took the height times the width for the parallelogram, it would be the same as the height times the width for the square. So in this case, both, if they had a 5-inch width and a 5-inch height, both the square and the parallelogram would have 25 square inches of area. We'll skip the volume of a cylinder. So we already pretty much did the volume of a cylinder. We converted it into a cone by multiplying the volume of a cylinder times 1/3. So next is the trapezoid. So trapezoids always have two horizontal members, A and B, and the base is longer than the upper member A, then we just connect the points so we get a parallelogram. So we look at the height. So imagine, assume the upper member is 5.5 inches and the lower is 9.8 inches. So, and the height is 2.8 inches. So we find the average value of the A and B and then multiply times height, then it would be the area of the trapezoid. But the shortcut just consolidates that formula. So it's 0.5 times A times height plus 0.5 times B times height. So if we solve for each side, we get these two values, we add them together. So for 21.42 square inches in this case is the area of this trapezoid. So we can check using the conventional method. So A plus B divided by 2, that's the average width of the upper and lower members, then times the height. So we calculate the same value as well. So now we move on to the volume of a sphere, and typically this is usually volume of a sphere is equal to 4/3 pi r cubed. But we could convert the 4/3 into 1.33, multiply this times pi, 3.14159, and then convert our radius into just d divided by 2. So radius cubed is d divided by 2 as a quantity cubed. So then we get d cubed over 8. So if we simplify, we multiply 1.33 times pi. Then we further simplify and just reduce this down to what we have on the shortcut, 0.5236 d cubed. So that one expression can also solve for the volume of a sphere. So if we check it, 14-inch diameter sphere, so 14 cubed times the constant 0.5236 solves for 1437.76 cubic inches of volume for the given sphere that has a 14-inch diameter. So if we check it with the conventional method, 4/3 times pi times r cubed, so 14-inch diameter divided by 2, 7-inch radius cubed, times pi times 4/3, we also solve the same value, 1436.76 cubic inches. And then of course the pi r squared, traditional formula for the area of a circle. So we just take pi times, in this case, radius 7.5 inches squared, and we get 176.7 square inches. Now we use the shortcut method. We got 1 mil as in 1.785. So if we were to just take the d divided into 2 quantity squared, we'd have d squared over 4. And then we could multiply that times the 3.14159. So if you worked out the constant, it would actually be 0.785. So that's why it always comes down to 1 mil spec. So that's another shortcut. Just take 1 mil, 0.785 times d squared. And so that's the conventional method. Let's go back there a little bit. So that's the shortcut method versus the conventional method. So you get the same value, 0.785 times the radius times 2 for diameter, and then the quantity squared. And then lastly, we have the area of a triangle. So instead of memorizing the formula for this one, you could just like look at a square or a rectangle. We'll start with a rectangle. and then we'll place a square. So if we were to divide the area of both the rectangle and the square across a hypotenuse and then erase one side, we could clearly see that the area of a triangle is just simply the area of a rectangle or the area of a square divided by 2. So base times height divided by 2, or 0.5 times base times height. And so sometimes it looks too simple to be true, and we may want to test the method through trig, law of cosine, law of sines, but then again, you can do so and you'll come up to the same value as you would using the base times height divided by 2 method. But if we look at the area of all types of triangles, it's still going to be 1/2 base times height. So we took the equilateral triangle and then the isosceles triangle and then the scalene triangle and of course the right triangle. So we could identify the base and the height components of all 4. So if you were to multiply the base times the height divided by 2 of all 4, you would still come up to the same value if you did it analytically using the law of cosine or the law of sines and trig. So it's just 0.5 times base times height. So this could also be used for other formulas that have too many components. Their constants can be multiplied and then distributed across for simple one-line shortcuts as for formulation. Thank you for watching this presentation and have a great day.